Okay, we're back again. Theorem 4.5, this is just a definition. It's a definition of an integral as an area. It says if f is continuous and non-negative on a closed interval AB, so it has to be continuous and non-negative on that interval. So maybe I'll just do something like that. So here we have a function that's continuous and non-negative on an integral AB. Then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and b. This area is given by this notation. It says the area is equal to the integral of f of x dx from a to b. This is called a definite integral. It's a definite integral because it has bounds on it. The indefinite integral, remember, was just giving us antiderivatives. When we evaluate a definite integral, we're going to get a number, right? We're going to get an area. So they're very different. Okay, so this is just a definition. It says we're going to define area, or this is area if the function is non-negative on the interval and continuous. Okay, let's go to our problem that we had. We had the integral then. We found the integral from a to b under the curve f of x equals to x. F of x equal to x certainly is continuous and non-negative on that interval. So we found the area as b squared over 2 minus a squared over 2. And so I pointed out before that both of these are antiderivatives of x, right? And this is what leads us to the fundamental theorem of calculus. It says if f is continuous on an interval AB and f is an antiderivative of f, then the definite integral the definite integral of f of x dx from a to b is given by f of b minus f of a. And that is the fundamental theorem of calculus. Okay? I did not prove it, but hopefully we walked through enough things that we're leading to suspect that it's true. Let's do an example. Find the area of the region find the area of that region. The function is 2x squared minus 3x plus 2. And so let's set up the integral. The definite integral is the integral from 0 to 2 of 2x squared minus 3x plus 2. And our variable of integration is x, so we put dx there. And now how we do this is we first find the derivative, or the antiderivative, and I'm going to put it in some square brackets. So 2x squared, what is the integral of 2x squared? It is 2/3 x cubed. What is the integral of minus 3x? It is minus 3/2 x squared. And what is the integral of 2? 2x. And I'm going to enclose my bracket, and then I'm going to put my 2 here and my 0 here, and that is just notation that's telling me, okay, I'm going to evaluate this thing at 2, and then I'm going to subtract this thing evaluated at 0. Okay, so let's do the 2 part first. We have 2/3 times 2 cubed minus 3/2 times 2 squared plus 2 times 0. That's the first one. And I ran out of room a little bit. But the second one, we're going to put 0 into there, and that's 2/3 times 0 cubed minus 3/2 times 0 squared plus 2 times 0. Let's see. 2/3 times 2 cubed, 16/3. This is 6. 3/2 times 4. And that's 0, and this whole thing goes to 0. So 16/3 minus, uh-oh. What's going on here? Oh, this one wasn't supposed to be 0. This is I'm sorry about that. Hopefully you were yelling at me and I wasn't listening to you. But yeah, the first time we're evaluating everything at 2, then we're evaluating everything at 0. So this is 4. Why I got confused there is because I noticed that my answer was going to be negative, and that's not good. So, because this is an area, right? 16 thirds now minus 2, so 10 thirds. That is the area under that fancy curve. Pretty cool, huh? You might, maybe I'll do another one. You might ask yourself, what happened to the constant of integration? Remember that when we did indefinite integrals, like the integral of 3x dx, we got 3 halves x squared plus c, right? Because an antiderivative is any number c will be an antiderivative of 3x. So what happened to the c? Well, let's look at that real quick. Ha! And it says it right there. What happened to the constant of integration? I'll show you. So, if we do the integral from a to b of f of x dx, we're going to get an antiderivative, I'll call it capital F of x, and, capital F of x plus c, and we have to evaluate that at b and then at a. So we have f of b plus c, that's the first one, and minus f of a plus c. And when I remove the parentheses, I have capital F of b plus c minus capital F of a minus c, and the c's disappear, and we don't have to worry about them at all. Yeah? Good. So that's why we don't have to worry about them. One more real quick. How about this one? You're going to like this one. How about we find the area underneath the cosine curve from 0 to pi? Let's see if we can see that. Oh, good, you can. So let's do it. The integral from 0 to pi of cosine of x dx, and now they're asking you find an antiderivative, right? Find a function whose derivative is the cosine. Oh, you say the sine. Good. And I am going to put that in brackets and put my these are called my limits of integration, and I'm going to put them there. So I have the sine of pi minus the sine of 0. What is the sine of pi? You go to your unit circle, you turn to pi, look at the y-coordinate, oh, it's 0. And what is the sine at 0? Zero. Oh. Huh. Okay. I kind of messed it up. See, this is why I try to make the videos shorter, because now it's too dang long. Let's do it again. And actually, I didn't do that right, did I? Do you guys know how I screwed up? I said, let's find, well, I drew the sine curve like this, but I called it a cosine curve. That's a sine curve. Let's find the area under the sine curve. Sorry, I was able to save myself there. Let's find the area under the sine curve from 0 to pi. And so first off, find an antiderivative of the sine of x. What is a function whose derivative is the sine of x? And hopefully say, oh, the opposite of the cosine of x. The derivative of cosine is opposite sine, so the derivative of the opposite of the cosine is sine. And we can do that from pi to 0. So we have the opposite of the cosine of pi minus the opposite of the cosine of 0. What is the cosine of pi? You turn to pi degrees and look at the x-coordinate, it's -1 there, so we have the opposite of -1 minus the opposite of the cosine of 0. What is the cosine of 0? It's 1. So the opposite of 1 plus 1. The opposite of -1 plus 1. 2. So the area under here, from the area under the sine curve from 0 to pi is 2. Okay, so that's all that. Remember that I skipped a lot, so I wanted to give you some examples that show you where the fundamental theorem of calculus comes from. You will be responsible to use the fundamental theorem of calculus and apply it appropriately. You're not going to be responsible for filling up an infinite amount of rectangles under curves. If we had more time, we would, but I'm sure you're okay with it. So, good job. I love you. We'll talk to you later.